Good afternoon, and first of all, I would like to thank to the organizers for inviting me and for the opportunity to discuss with you our research and to continue in this discussion on the ab initio R matrix method and on the vibrational frame transformation for the neutral molecules. So this will be, in some sense, kind of continuation of Chris's talk and also of Jonathan Tennyson's talk. First of all, I would like to acknowledge the funding of our research by the DOE, and we started with this project at GILA, and now recently we moved to the Purdue University. The theoretical methods of electron-molecule scattering can be in principle topically divided into two categories. The ab initio methods that are using the molecular electronic structure theory to treat the electron-molecule scattering in the fixed nuclei approximation and that deal with the electronic structure, and the methods dealing with the vibrational and rotational dynamics of the nuclei. And both types of methods have their own set of issues and their own set of goals. For example, with the ab initio method, the ab initio methods, they aim to treat more complex molecules with more complicated electronic structure, polarization effects, larger number of valence electrons or molecules that have lower symmetries, and so on. And the vibrational dynamics of the nuclei, these methods aim to treat systems with multiple vibrational modes that are essential even in rather simple systems, as we could hear yesterday. And there are still some quantities that cannot be really routinely calculated, like the branching ratios in the dissociative recombination. And in my talk, I would like to kind of share with you some ideas and some of our experience that might help in the future to address some of these issues and to achieve at least partially some of these goals. So first, I would like to discuss the molecular R matrix calculations in the fixed nuclei approximation, and I would like to talk about the one particular choice of the set of molecular orbitals that can help in certain situations to model the interaction properly, and I want to talk about the alternative method of calculation of the R matrix from the inner region Hamiltonian that does not involve the diagonalization as it is usual these days, but that is based on the solution of the system of linear equations. And from there, I would like to move to this energy-dependent vibrational frame transformation and show how these two types of calculations, how these two approaches can be connected. And I would like to discuss a bit the vibrational excitation and the photodetachment. I will demonstrate these ideas and these approaches on the electron interaction with the oxygen dimer. Why oxygen dimer? It has rather challenging electronic structure. The ground state is triplet sigma G minus. It's an open shell system. It has quite low electronically excited states. The lowest excited state is singlet delta G with the threshold around 1 eV. The mean polarizability is 10 atomic units of polarizability, and O2 minus and O2 can capture an electron and create a bound state with this electron affinity, And this bound state is predominated by the electron correlation, or it's entirely the correlation energy. In addition, that was actually the initial motivation of this research. In this work, Maps and his collaborators published the vibrational dependence of the anisotropy of the photodetachment cross section. So let me show you some eigenphases in the fixed nuclei approximation in this doublet pi G symmetry for the equilibrium geometry of O2. In these three models that are discussed here, we used the atomic natural orbitals Gaussian basis set and complete active space SCF molecular orbitals for neutral O2, for neutral oxygen. In all our models, the 2 sigma G and 2 sigma U orbitals are doubly occupied in all the configurations. So this is the complete active space for this model number 1 that is represented by the red curve, and you can clearly see here the resonance. In the close coupling expansion in the inner region, 128 target states were included. Mainly, vast majority of these target states were in triplet pi U and triplet sigma U minus symmetries that contribute to the ground state polarizability. So the idea was to somehow have better representation of this polarization effect. And we clearly see here the resonance behavior around 0.8 eV. However, the experimental value for this resonance is around 90 milli eV above the threshold. The first idea was that probably the polarization effects are still not converged, or that this close coupling expansion is not converged with respect to the number of target states included. So I included more target states from all the irreducible representations. I released the restriction of the non-zero dipole coupling with the ground state, and indeed the resonance moved slightly lower, but not enough, not much, and it stopped here. So then I started to speculate a bit about the orbitals, that maybe I'm missing some really important orbital in the complete active space. But when I replaced, for example, this triplet pi U orbital by the 4 sigma G orbital, the change was not too impressive. And since we perform everything in this complete active space CI approach, this space of active orbitals is rather limited. So what I tried next was to use the anionic orbitals instead of the orbitals for the neutral, and although these results of these previously shown models were in good agreement, were consistent with previously published R matrix calculations. Actually, when I moved to these anionic orbitals, the resonance moved down, and it moved to 0.15 eV, what is in much better agreement with the experiment than all these calculations before. And I was still able to use the same complete active space as in the previous model, as in the model number 2. So the total size of the Hamiltonian is still quite modest, and the calculation is still quite tractable. However, I had to include these 528 states in the close coupling expansion to get this position converged. Of course, as was mentioned here before in several talks, in the scattering calculations, we always have to represent the n particle target state and the n plus 1 particle scattering function in the same basis set, using the same basis set. So if we use the basis set optimized for the target, it won't be optimal for the n plus 1 particle wave function and vice versa. So as long as our orbital set is truncated, and as long as our CI expansion is truncated, what pretty much means as long as we are living in a non-ideal world, this will be in some sense an issue. And in this case, the use of these anionic orbitals, of these anionic molecular orbitals, really helped. Also, this is just one particular case of the selection of the orbital sets. For example, in the UCL group in this work, they used the natural orbitals of really extensive MRCI calculation of the target. Or this work by the Berkeley group used Slater transition complex orbitals that are projections of the n plus 1 particle and n particle orbitals. It was in I think photodetachment of HOCO. So this is another choice that helps to keep the model tractable and that helps to reproduce the correct fixed nuclei physics or reasonable fixed nuclei physics, and still to keep the calculation tractable. Here you can see the comparison for different internuclear distances for different geometries. You can see that model number 1 actually cannot really yield the bound state of O2 minus, while this model based on anionic orbitals can reproduce it rather well. Here you can see the comparison of the electron affinity with the experimental value. And this use of these anionic orbitals, it does not perturb that much the other quantities that are essential for the nuclear dynamics, like the vibrational frequency or the relative position of the minima of the potential energy curves. So here you can see that also this model based on the neutral orbitals agrees well with previous calculations, with previously published R matrix calculations that were much more modest than this model number 1. But anyway, just simply the increase of the size of the Hamiltonian was not too helpful, but this alternative choice of orbitals helped. The other idea I would like to kind of touch, or I would like to discuss a bit, is the treatment of large complete active space models. Because in addition to the choice of the orbitals, of course, the aim or the intention is to deal with larger and larger correlation models and CI spaces. As the UK R matrix code, as it is set up now, it works in the following way: that first the inner region Hamiltonian, that is the sum of the Hamiltonian matrix and the Bloch operator, first it is completely diagonalized, and then the R matrix can be calculated using this rather simple formula. Of course, this is very simplified notation, just to show the spirit of the method. The advantage of this method is that you have to diagonalize the Hamiltonian only once, and then the R matrix can be calculated for arbitrary energy. However, this step is rather demanding, and this method, since you have to perform complete diagonalization, can run out of the steam rather quickly. So in order to overcome this difficulty, the partitioned R matrix has been introduced, where only part of the spectrum is calculated accurately, and the rest is replaced by one effective R matrix pole and one effective amplitude. It was introduced in this work, and it is used these days. The method I tested, and the method we kind of are dealing with, is based on the solution of the linear system of equation instead of diagonalizing the Hamiltonian. Of course, we lose the advantage of performing this step only once. So we really have to solve the system of equations for each energy, for each scattering energy of the interest. However, we gain the advantage that we can use only the sparse matrix storage, and we can use rather efficient sparse solvers. I tested Paradiso. And it's more straightforward to implement this in the parallel computing environments than the diagonalization methods, than the diagonalization techniques. I used, just as a demonstration, I used this approach to check whether in these models where I use the neutral orbitals, whether I'm not missing something important, or how far can I go to how the position of the resonance will decrease with the increasing number of orbitals. And in this model, I was able to get to treat the Hamiltonian with this dimension, 126,000. And actually, the results were pretty much the same, like this much more modest, much smaller model based on smaller complete active space. Of course, with this method, what matters in addition to the total dimension of the Hamiltonian is the density of the matrix, and as the size of the Hamiltonian is increasing, as the size of this complete active space increases, usually the matrix becomes more and more sparse. So I would like to discuss the form, the good form of the solutions in the outer region, or the form of the solution in the outer region that is suitable for the treatment of the nuclear dynamics. Just to keep it simple, I consider here only single scattering channel and single partial wave, but of course the generalization to the multi-channel approach is very straightforward. So what we usually do is that the solution in the asymptotic region can be parametrized using the eigenphases that determine the linear combination of the regular and irregular spherical Bessel functions. However, if we slightly rescale these spherical Bessel functions to functions that have energy-independent behavior near the origin and that are not energy normalized, then we can parameterize the solution in the outer region using the quantum defects, using the smooth quantum defects. And these quantum defects have such a property that they are smooth through the thresholds, and they are well defined also for the negative energies. So here you can see the comparison of the scattering eigenphases and smooth quantum defects for the doublet pi G symmetry of O2 minus. So even in the when the scattering eigenphases show a rather rapid change with the energy, the quantum defects are still quite smooth. Of course, in this symmetry there is no resonance, and the the eigenphases for different internuclear separations are smooth, and so the smooth quantum defects are as well. So this kind of suggests that there is a method of the nuclear dynamics that might allow us to treat the resonant and non-resonant cases, the scattering in case of resonance and in the absence of resonance, in a similar way. These quantum defects can be also used to determine the bound state of the negative ion using this equation, and basically the energies can be determined as the intersections of these curves, and these curves they are quite smooth for small negative energies when the state is weakly bound. So these smooth quantum defects, they are suitable quantities. They represent the suitable parameterization of the fixed nuclei problem for the energy-dependent vibrational frame transformation approach. So as Chris mentioned in his talk, for the positive ions, the quantum defects, their dependence on energy is rather small. In case of the neutral molecules, we cannot really neglect it. So this theory, as it was developed and published in 1990 by Hong Gao and Chris Green, is based on the assumption that in the inner region the Born-Oppenheimer approximation can be still valid inside the reaction zone. So when the electron enters the reaction zone, it still will be accelerated sufficiently that the Born-Oppenheimer approximation can be applied, and the n+1 particle Schrödinger equation can be separated in this way. However, without imposing in advance the boundary condition of the outgoing electron on the surface of this reaction region. And since we don't have this this boundary condition for the electron, we don't really have quantization, prescribed quantization of these potential energy curves. So there is some arbitrariness in their determination, and in this approach and in the approach I'm using nowadays, they are chosen to be shifted potential energy curves of the neutral. So this is the R-independent constant that does not depend on the internuclear distance, and it actually says that the basis, the adiabatic basis of this problem is constructed in such a way that the electron does not feel any additional force when the continuum electron does not feel any additional force from the molecule. So outside the reaction zone, the general solutions of the Schrödinger equation can be expressed as the vibrational close coupling, as the vibrational close coupling. And in the inner region, they can be represented using this Born-Oppenheimer approach, and they can be parameterized using these fixed nuclei body frame quantum defects that are calculated ab initio. And the matching of these two solutions on the boundary of the reaction region allows us to determine these I and J matrices, and this formula determines the MQDT short-range K-matrix that can be transformed into the physical K-matrix using the standard MQDT procedures of elimination of the closed channels. Of course, to make this working reasonably well and to have all the matching integrals evaluated, these quantum defects need to be reasonably smooth. Otherwise, really dense energy grid is necessary for the quantum defects, and this method starts to have some problems. So let me very briefly show you very preliminary results for the vibrational excitation of the oxygen dimer calculated using this vibrational frame transformation in the doublet pi G symmetry. So it's the symmetry where you have this low resonance that I showed here. Yeah, so in this doublet pi G symmetry, you can see these very narrow peaks and these very high cross sections in the elastic and vibrationally inelastic cross sections. And of course, as you go to higher and higher vibrational states, the cross sections decrease. And here is comparison with the previous theoretical work that employed the non-adiabatic R matrix theory for the nuclear motion, and with the fields experiment. Oh, I just forgot the reference. It's a paper from 1990. So here you can see that the comparison with those results. Of course, what I'm working right now on and what I'm dealing with, what is the goal of all this project, is to treat the photodetachment of O2- and to deal with the vibrational dynamics of this process. So the step I'm working on right now is the vibrational frame transformation of the body frame transition dipole matrix elements that are calculated in the fixed nuclei approximation, and then using this, I will be able to calculate the differential cross section into different vibrational states, into different final vibrational states of the neutral, and to determine this anisotropy parameter and to compare it with the experimental work. So to conclude my talk, I was talking about the ab initio R matrix calculations of the bound and continuum states of O2-, I showed that the molecular orbitals of the negative ion yield more accurate position of the doublet pi G resonance and of the bound state than the orbitals calculated for the neutral. I demonstrated the method of calculation of the R matrix based on solving the system of linear equation, and I showed how we can calculate these smooth quantum defects and how these are connected to the energy-dependent vibrational frame transformation that allows us to calculate to deal with the vibrational excitation of the oxygen dimer, and that allows us to perform these calculations of the photoelectron angular distribution in the photodetachment process. So I would stop here. I would try to answer your questions, and thank you for your attention.
So I saw that the molecular orbitals of the negative ion in the CAS yielded better results, but do you know why they yield better results than using the
A little bit. I'm still working on the interpretation of this, but first of all, the anionic orbitals, they might be more diffuse than the neutral, and they might allow the additional electron, to go farther in that basis, and somehow to represent the polarization effects better. The other kind of speculation I have is that we have n+1 electron wave function, and we have n particle electron wave function. So maybe the n particle electron wave function can converge faster, or can converge in smaller basis set of the CI of the CI configurations than the n+1 particle. Yeah, something along these lines.
But in the anion, you didn't add any diffuse basis functions to the valence basis set, if I understood correctly.
In the anion, well, I did not, because in the R matrix we have this set of continuum orbitals that are non-zero on the boundary, and this very diffuse behavior, these cases when the electron has to really go far from the nuclei, is taken care of by the closed channels and by all the R matrix procedures. However, in some sense, they are there, because these continuum orbitals, even in the inner region, they represent the states of the n+1 particle system when the electron goes farther, even when it doesn't really go outside of the R matrix box. So the continuum states are there, the continuum orbitals are there.
I believe, I think people like Barry Schneider and stuff did something very similar years ago for Into.
Oh, yeah.
Resonance in the right position. What they did in those cases is they, if you try and do an SCF calculation, M2 minus just collapses in a big basis. So they would use this basis without too many diffuse functions, do an SCF, stop it after 2 or 3 iterations, and then diffuse those orbitals in a scattering calculation. And they essentially, you get the resonance spot on. This sounds to me the spirit of this is resonance. Yeah.
One thing I'm wondering, if you go back to your results for the resonant vibrational excitation, the other, you're getting the position sort of like the previous calculation being that fast.
Which one?
The Higgins. That's the Barry still where the DL that's
Right. Yeah.
Is what, and this goes back probably before you were born, people would try to do vibrational closed coupling for excitation in the presence of a resonance. They were using the wave functions for the ground state, and they have to do a lot of terms to converge, because what they
Talking about
actually
Aaron
wanted to do
Hempkins' model?
yeah, because what they wanted to do was it wanted to look more like the anion, the real wave function, the vibrational motion was more like the anion, and then that's why, and so they had put a lot of functions to convert. Are you using when you do your frame transformation, you're using the neutral bit?
You mean the vibrational eigenstates? Yeah. Right now I'm using I'm using the neutral.
You might go look at that third work, because they really it took forever to convert.
Yeah, I'm actually kind of considering some ideas how to employ the vibrational states of the anion, and I thought that also Christian Jungen had something along these lines as well. So that's something what I keep in mind and what I would like to dive into more. But to comment on this a little bit on this disagreement, like that as you are saying that this calculation is doing better. Actually, what they did is that in their fixed nuclei calculation, they artificially, they by hand shifted the R matrix poles. They adjusted them. They adjusted the fixed nuclei R matrix poles, and I don't exactly know what was the criterion of this adjustment. So there was kind of adjustable parameter to have these things better, and I don't have any of that. And also, as I said, these are preliminary results. They need to be checked more, and they have to be analyzed further.
The experiments resolve the spin-over level?
Excuse me?
In the experiments, either one resolves the spin-over coupling?
I don't remember it does. I don't think so. I don't think so.
I thought even in the low energy electron scattering was because it was even resolved. This thing.
From Michael Allen?
I can't remember. But I don't understand.
I remember.
Photodetachment one should definitely be able to.
These vibrational peaks in the experiments are so sharp we don't really know what the cross-section is.
Excuse me?
Vibrational peaks in the experiment are so sharp that they don't really know what the cross-section is, trying to resolve the delta function.
That's the case of this experiment. Then there was a very old experiment by Linder, where he had really very wide peaks, and there were some more photodetachment experiments that had narrow peaks. So I'm slightly puzzled by this experimental data. But I remember that there was one work, I think it was by Tyler Billy, from I think 70s, late 70s. I'm not sure, and it was dealing with the spin orbit coupling. But I think that it was just a theoretical model. I don't recall any experimental results on the spin orbit coupling.
I also want to ask about experiment. You refer to Richard Marx. So he apparently studied the dependence on vibrational state for the detachment cross-section only, yeah? And so I understand that you don't have results yet, but could you briefly summarize what is it strong dependence on initial vibration state?
Maybe I could simply pull out the graph.
I think it was fairly gradual beta parameter versus leading.
Right. Yeah. There was no sharp. There was no. Oh, I see. This is something what is showing the dependence of the beta parameter on the photoelectron energy. Basically, their aim or the goal of the paper is to understand the technique and to develop a method how this anisotropy could probe the vibronic coupling in the negative ion.